Well, thanks for coming. Some of what I'm going to cover has been very eloquently covered by Joshua, and Yao-Ming, but hopefully hearing it again will help drill it into everybody that, we really tried to make this a standard by which you can take anybody's card and put it in anyone's system, and that bad things don't happen.
The final slide deck. Okay.
So we're going to talk a little bit about NIC design. Sumit's going to come up and talk about some electrical validation, and then Rick Eads from Keysight is going to talk about test methodology and test setups. And we have a live demo here from Keysight that will be here a few minutes after, I think. And then Broadcom actually has brought a working NIC 3.0 and a server chassis showing the shared LOM functionality through systems management. So we have some good demos here. Thanks to both companies for doing that. So Ja did a really good job. The one thing that I would say that he said was that the NIC 2.0 spec wasn't very good, and I would say that it wasn't intended for what we used it for. And it wasn't a quality issue, it was a fact that it went well beyond the scope of what it was ever intended to. But in NIC 3.0, what we're trying to do is create an interoperability spec so that the NIC suppliers, who many of them are here, only have to make one piece of hardware, and we can differentiate in other methods and other means. So we have a clearly defined form factor. As Joshua mentioned, we have solid 3D models. We also have 2D critical to function dimensions in the spec so that we have a way to validate through whatever means the system vendor or the card vendor wishes, the manufacturability of the card across something like CPK, capability studies, if that's required. The other thing is, thanks to HPE and TE, and where Rosh is, but, they're by Mike, these guys got the 4C plus connector into the SFF TA1002 spec in less than 2 weeks. And so we actually have an industry standard connector that's documented, and you can go to the website, the SNEO website, and pull it off. So that's really a huge step in getting that released into the industry. From a systems management perspective, again, Himmel, Yuval from Mellanox, a bunch of people really contributed here to refining the systems management. One of the things about systems management is we're not trying to put everything in as a default. But there's certain aspects as a system vendor that I need in order to make sure that I don't blow up your card or you don't blow up my server. Thermal information, power information, those are the types of information that the systems management is going to guarantee as a baseline to allow me to take a new vendor, maybe some small company, they provide a NIC, just plug it in and try it. As long as they're compliant, the system's gonna understand how to handle that. And if it can't handle it, then it won't turn the card on. So we've made a huge step forward from a system perspective. It's a huge step forward because I can predetermine whether or not to turn the card on and if I can support it in system. So I have a little graphical representation of what Joshua showed about card sizes. So on the left, you have a low profile half height or half height, half length card, and the small form factor. There's about 20% difference. One difference between what I said and what Josh said is the small form factor and the OCP2 are about equal. The small form factor actually is more usable space because of where the Bergstack connectors were, and they took up so much top and bottom space. But the actual PWB area from square millimeter perspective is about the same. So we're in a better spot with 3.0 than we were with 2.0, even though the actual square millimeters is about the same. The other thing, and he mentioned this, but to me it was really critical. If you've designed a system or card around 2.0, there's like 13 different Z height keep out areas that you have to be able to move parts around, and that part is 0.1 over there. And so nice, very simple shaped keep out that I think will ease layout guidelines for the NIC vendors and make it much easier to fit it into a server. And then, of course, on the large form factor, you know, it's the numbers are there. I'm not going to bore you with them. One of the things that I will say is this is better thermally, as Yoming said, but it's not as good as a PCIe card because of our keep out heights. And so there is still a huge demand going forward for low profile PCIe cards and full height PCIe cards, but low profile to compare with our small form factor, because you can get another, 4 millimeters, 4.17 millimeters of height on your heatsink, which is a huge amount for the thermal aspect. So we've made dramatic improvements, and then Yao Ming explained how that could be extended in the future because it's facing up now. Well, you can do something custom with a faceplate and your chassis, and you can have a handle more power on the card. Sorry. So, just a brief overview. I don't know if any of you were able to make one of the systems management talks, but these guys did a really good job. So from a power standpoint, we don't have a traditional PCIe card power state. We have an ID mode, an aux mode, and a main mode. During ID mode, you're going to be able to read a FRU EEPROM, determine if you can power on the card. In aux mode, you get a list of shared LOM features, wake on LAN, and you get a higher power than what PCIe cards use in their VAUX mode, which is limited to a single pin, 375 milliamps, or, you know, what is that, about a watt, 1 point something watts. And so you have a much higher power envelope in our aux mode than what's available on a PCIe card. This is because these are used in a lot of servers for LOM devices where you want shared management and you want wake on LAN, even if you have a 100 gig port, because that's the only way you want to access your server. From a thermal standpoint, the FRU contains some key thermal information, but then they have a required thermal reporting mechanism that was worked out so that your BMC can make rational decisions on what's going to happen in the server with the card real time. So we talked a little bit, talked a little bit about the tiers. What I have on the top there is the PCIe tiers that are part of a PCI SIG PCN that went through, that was accepted. And I put them there for reference. And I put the table at the bottom because she made a really good point. We're still collecting a bunch of data, especially Hot Aisle, because Facebook's doing a lot of the cold aisle work. There's other companies, HP, Dell, et cetera, doing Hot Aisle. And that's why we did this test fixture. And the key here is it still is a work in progress, but we know that we're better than 2.0. So we know where the worst case is, and we just have to see how much better we are. The interesting thing is we tried to make this simple, this test fixture. I encourage you, if you're interested, if you're a card vendor, come up, play with it. I know it's not assembled. It came in Friday morning, but play with it and then get your feedback into the thermal teams work group, because Dell is willing to change that so that we can have one test fixture for the community, and we'll contribute that to the project. So from simulation mainly, but we also have done some thermal test boards, which are using the TimberCon loopbacks and some heaters. We've got some areas that we know that we're going to have problems or need extended temperature optics. Again, it's it's kind of an eye chart, but basically what we wanted to do in this first generation, probably releasing sometime next year, is 25 gig was a requirement with optics in the hot aisle, and 50 and 100 gig were stretch goals. And 25 is not a problem. You can see evidence of these cards in the expo down here. We know those are going to work, and we're working on the 50 and 100 right now to see what do we need to do on a system level to get those cards to operate. So, quickly, standardization for thermal testing for card vendors. From a systems perspective, what I'm going to do is I'm going to test my chassis I'm going to know at what point my chassis fan PWM matches the thermal test fixture, and I'm going to set it that way based on the information that the card gives me initially. Then once the card is operational, systems management is going to tell me what the actual temperatures and margins are, and the system can then modify the fan speeds to keep the system cool. And I think that's pretty standard across the mainstream server vendors today. But now when the card vendors test their cards, they can all test using the same test fixture so that vendor A's data and vendor B's data, if it says the same thing, you know how to adjust for it in the system instead of, well, they use this type of test fixture and vendor B used this type, and oh, they really don't correlate at all. So a common methodology, and you're going to see that in Sumit's presentation as well from the PCIe validation. So trying to drive that to where everything is standardized. Sorry, and now Sumit will come up and talk about PCIe validation.
Thanks. Thank you, John. So like as John indicated, yeah, so we would like to actually standardize our validation strategy across all, both the thermal and including the electrical part. So there has been a lot of, like in the historically, like with the OCP 2.0, as Ja was indicating, so the specs have been very loosely defined. So we don't, there was not much effort or not much innovation done to help define how do we validate the electrical aspects of the system. So in the keynotes, I'm sure you guys must have heard, like the OCP ecosystem is now growing, and this basically puts more need for a more standard way of us to be able to validate how electrically they can interoperate. So one of the goals what we wanted to achieve was make sure that so whatever solution we come up with for the testing, so we wanted to make sure that it is any vendor, any system vendor, or any NIC vendor, or even a third-party lab, they can be able to adapt that. So that's the mindset we started to, we took that mindset and we wanted to use that to develop the testing and the whole interoperability solution, how we would like to achieve. So there was, like I was indicating, so the end goal for this effort is actually to help define a full solution for OCP 3.0, the NIC 3.0. So we would like to, Ja indicated in the roadmap, like, so the version 0.9, which will have the full SI guidelines defined. So we have a working group just started, a couple of weeks back. And so we are still kind of bringing that up. And we are trying to gather all the requirements and trying to formalize them, how the SI for this OCP 3.0 should look like, learning from what 2.0 lacked. There is also, so this is all being done, there's a big cross collaboration which is happening. So Dell is part of it, KVM is part of it, our friends like Keysight is part of it. So there is, Intel is there. So we are so all these people are kind of working together to help define for the how do we solve this problem for 3.0, sorry. So one question is like, why, if we take a step back, like why do we want to define this kind of a standard method? So this is a PCI interface. This is a standard interface. This is used, there's a big ecosystem out there for PCI. But one thing to keep in mind, the PCI ecosystem, what is out there, that's the CHEM ecosystem, what PCI SIG defines, that's very different from the OCP ecosystem. The OCP, so this is just if you look at the table on the right side, or the left side there, so there is, you will see that there is a certain subtle differences between the topologies, like for OCP, for the PCI CHEM ecosystem or the PCI SIG ecosystem, so it defines only for 2 connectors. But in our OCP ecosystem, we have systems which have 3 connectors. So the topology changes, the requirements are very different. So the channel, so we have to consider those deltas to understand, like, okay, how do those deltas impact our electrical interoperability of these NICs and the platforms? There is also, and even the system loss budgets are very different. Looking at what the CAM has defined, allocated for the motherboard versus what we can use for the OCP. So we are trying to use very different approaches to implement the PCI interconnects. This kind of creates a little challenging from the validation point of view. Okay, how do we validate now these interoperability aspects of from both the platform side and from the NIC side? So, but one thing which we wanted to keep was PCI has done really well defining the testing and electrical testing aspects. They have done really well to define, okay, what needs to be tested and how it needs to be tested. And we wanted to keep the same methodology and same philosophy. We wanted to bring it to the OCP ecosystem. And so we are leveraging a lot from the PCI CAM to be able to help us define, okay, how do we test in the OCP environment? So we are still using a lot of the parameters which we are trying to, in the first phase, what we're trying to target is like mostly for the transmit signal quality and the receiver jitter tolerance. There is also, and also using for receiver testing, so we are still trying to keep the same philosophy of using a stress tie. So if you're familiar with how the CAM tests for the receiver, so they use a very specifically defined stress tie to test the receiver sensitivity. So which is the same thing which we are trying to adapt. We are trying to bring it into the OCP ecosystem also. How do we do that? And Rick is going to talk in more details on how that is actually a little challenging. So now, and the concept, and like I was indicating, the concept of doing this conformance testing, we wanted to keep it same. So there is two basic tests which we are trying to focus right now is the transmit signal quality and also the receiver sensitivity and the jitter tolerance. So that's how we are starting slow, small, and then we will eventually try to bring out more there's a PLL bandwidth testing which is also part of the PCI electrical testing, which is right now kind of is not in the scope of work at this point. But the concept is very similar. So this is actually the setup what is showing here. This is the actual setup for the transmit signal quality assessment. And I think Russ has a good setup out here, and he'll be able to show you more details, and Rick is going to talk more. So now just to talk about how we are going to achieve that. So what we did, PCI SIG has defined a very specific test fixtures to be able to do the transmit and the receiver testing. And those are the fixtures right here. You can see it in the green. So these are the baseboard fixtures, and there's a riser board. So we tried to use a similar concept, and we applied it for our OCP platform. And so we built actually three sets of boards. So these are boards here, sorry. So these are the load boards. So there are two sets of load boards. So because of the OCP,
we have a backup.
Thank you. Thanks, Rick. Thank you, Rick. So yeah, like I was saying, so what we did is, so for OCP ecosystem, so we started off with 2.0 mezzanine. So the reason we started with 2.0, one is we have a good, well-established user base. So there's a ecosystem out there which we can use to understand what are the things which we need to address as we go into 3.0. What do we need to be able to help solve that problem? So we started with 2.0, and in 2.0 universe or ecosystem, we have three sets of board test fixtures. So one is for there are two types of load boards. There's a load board for type A board connector, and there's a load board for type B connector. Then there is a baseboard. And from feature function point of view, they are very similar to the standard PCI SIG boards, like what they have for the CLB and CBBs. And along with that, then each of these boards also have the calibration boards, which we defined to be able to help calibrate. So each test fixture can be calibrated independently. And just to introduce to the 3.0 world, so this is thanks to John and from Dell. So they are contributing the 3.0 fixtures, which is on the similar concept and similar philosophy, similar design. What we use for 2.0, we are leveraging that learning going into 3.0. So these 3.0 fixtures, they are designed very similar to what 2.0 fixtures have been designed. So there is, again, like 2 sets of board in here. So there is a load board, but load board there, you can see there are 4 actually independent boards. So each of them is by 8, just given the physical aspects of the 3.0 form factor. So we had to break it down into 4. And so each of them are by 8. And these are the load boards, and there is actually, they have the calibration or for measuring the loss per inch. And then similarly, there is a baseboard. So this is also out here. So you can see physically. So this is the load board. So there are 4 panels. And this is the 3.0 baseboard. So right now, you will see that the connectors are actually missing. And I think John probably can talk more about that, why connectors are missing, because they were not available. When? They're still in transit. Oops. So just going in a little more detail into the design of these fixtures. So what we did is, so there was a challenge, like, because these systems are already designed, and we had to consider that, okay, we are using these OCP 2.0 systems in field. And they have been running for quite some time. So we are still trying to understand, like, how do we break down the budgets between the baseboard and the load board? How do we break it down across the 2 fixtures? So we started off with, we considered a lot of different aspects, like the material, what material should we use? And they, as you can see from here, like both 2.0 and 3.0, they're using very similar materials. So 2.0, the baseboard actually uses mid-loss, whereas the 3.0, the baseboard uses slightly low-loss material. Correct me if I'm wrong, John. Yeah. And the load boards are both low-loss materials. The other aspect is, so all the channels on these, all the transmit and receive channels, they are actually equal length. So we designed these such that they all match within 1% of each other, so that this was mostly to help us with designing the calibration board. So now in the calibration board, we can just design for 1 channel. And so we don't have to worry about calibrating each and every channel independently. So now that we have a single channel, and all these channels are matched within 1% of each other. There's all, like I was indicating, like it's very similar to the CVB and CLB. So we have the clock trigger, clock toggle functions all built into these CVBs, so they can independently be used, like the way currently for the standard chem, how you use for testing the add-in cards. Just to give a little more insights into some of the design aspects of the 2.0 fixtures. So we did run a lot of simulation work trying to understand, like, okay, how much loss should we target? So we used our current existing platform base for the 2.0 systems in our field. And so one of the things which we're looking at, like around 14.5 dB of loss, which would be a good for baseboard. And for load boards, we thought about like 3.5 dB based on the existing designs what have been done. And so we just got we just received these boards like 2 weeks back. And they are so our partners in Taiwan, so they're helping us do all the testing and validation. So these are results just came out. So we are looking so the actual test data is looking very close to the design targets what we had. Then we also looked at, took the 2.0, these designs, these fixtures, and tried to understand, okay, how does that impact the channels in a current platform, in the existing platform? How much margin do we have? So right now, the actual measurements are still under works, but we have the simulation data which is showing that we do have enough margin, both in the add-in cards and also in the system. So we have enough margin So we're able to meet the interoperability of the from electrical point of view. Just to give a more quick insight into how the calibration boards were designed. So each of these calibration boards, they are uniquely designed for each fixture. In the sense, so this is a typical calibration for board for the load board A, which is type A connector. And this board and the actual fixture, they are actually built into the same panel. So if you're familiar with how the panelization happens for the PCBs, so they are actually from the same panel to basically to reflect that they are going through the same manufacturing process. So whatever the variations are, they are common across both the calibration and also the fixture. So when you do any calibration using the calibration board, so you have enough confidence, okay, they are reflective of the actual test fixture. And they also are serialized. So each of these fixtures, they're uniquely serialized. So you can identify for each test fixture which calibration board is used. The reason what I was indicating earlier for the calibration board is to help us calibrate out for each fixture, like how much loss or how much loss do we need to consider when we are doing the measurements. And this helps us with that in the sense, like since I was indicating, so the length on the channel length on the calibration board is the same length as the fixture. And so it's kind of a 2L philosophy what is kind of used, where you are measuring twice the loss, and then you divide it by 2, so to get the actual loss of the channel. And that helps us to be able to kind of understand, like when we are doing the measurement, okay, how much loss is there. So this is, so this is still a work in progress. So there's still a lot of work which we need to do since the fixtures were just received 2 weeks ago. And so we are working very closely with our partners here with Keysight to help us understand what is the test solution would look like for both the 2.0 and 3.0 going forward. So we are starting with 2.0 work. So we are using the existing platforms. So we have the Bryce Canyon. I'm sure you must have seen out there. So we have the Bryce Canyon as our storage platform, which we are using. Then there is a Yosemite V2, which we are using for the load board, which is type B. And then the mezzanine itself, which we have for the baseboards. And Rick is going to talk more about the actual testing and what it takes to get the compliance testing done. Thank you.
Thanks, Sumit. Hi, my name is Rick Eads, and I am Keysight's representative to the PCI SIG. And I'm going to talk a little bit more about the specifics of leveraging PCI Express techniques and methods that we've developed within the PCI SIG for the car electromechanical form factor. And we're going to move that over into the OCP form factor that you see here. And I'll show you first just some of the examples of if this were a car electromechanical form factor, what kind of testing would you be doing? This sets the stage for the kinds of tests on the transmitter as well as on the receiver for the testing that's required under OCP. So in physical layer compliance, the focus is really on interoperability predictors. So we want to do the types of testing that's necessary to ensure that a vendor that has a motherboard made from, on one side will work and interoperate with an add-in card, a NIC, or even a storage device that's made by another vendor. So the two things that we do to help enable that are focusing on signal quality for the transmitter side and then receiver testing. The specification for PCI Express is divided into a number of parts, and each of those parts reflect a specific kind of conformance requirement that is comprehensive. So on the one side, you have a transmitter specification, you have a receiver specification, and then you have a channel spec. So each of these things can therefore be tested individually. And the theory behind this is that if you have a compliant transmitter and connect that to a compliant receiver through a compliant channel, then by default or by definition, the system is compliant. Now this becomes a really important concept when we look at Gen 3 and Gen 4 and even into Gen 5 with speeds up to 32 gigabits per second. It's very difficult to test a system once it's already been assembled. So you have to figure out a way that gives you predicts interoperability that allows you to assemble a system that is able to work at those higher speeds. Now, to do that, we have a number of spec documents. We have the base specification, the car electromechanical specification, and the test specification. So these are all documents produced by the PCI SIG that we would leverage to be able to write the equivalent test specification and form factor specifications for OCP. Now, from a channel perspective, that's really something that we consider that's critical for PCI Express. The Gen 3 spec, which is OCP 2.0, comprehends a channel that's about 50 centimeters in length or 20 inches, and that has 2 connectors in it. So you can see that server type channel being represented right here. There's also a shorter or client target channel, which is more reflection dominated, but I think for OCP, this is really the more representative model, which is more loss dominated. When we come to testing, we have a couple of different test fixtures, and both of these are represented in the OCP test fixtures that we have assembled here today. But we have a compliance baseboard, or CBB, that we use to test a system. So we plug in a card, a test fixture that represents the adding card, into the motherboard design. Then when we're testing the endpoint devices, or the adding cards themselves, we have a compliance baseboard that really forms the channel that's representative of the actual root complex device. And so these are the test setups that we would use, and we connect instruments like oscilloscopes to be able to test the transmitter signal quality with those fixtures. Here's an example of an in situ or a actual test setup from the workshop events that we've run, where we have here a graphics card that's plugged into the compliance baseboard, and this is an actual system that's plugged into where you have a compliance load board plugged in. Now the OCP form factor is substantially different than that mechanically, so we have different mechanical fixtures that have been developed to address the similar types of testing requirements for OCP. But the overall test method, what we're trying to do from a transmitter test and from a receiver test perspective, is exactly the same. So the test procedure then is to set up the DUT connected to the instrument. So the 2 instruments that are relevant here are an oscilloscope for the transmit test, and then an oscilloscope and a bit error rate tester, or a BERT, to do the receiver test. So for transmit test, we cause the device under test to generate a compliance pattern, which is a transmitted signal representative of actual data at the data rate. We capture that on the instrument, and then we post-process that data to determine what the eye width and eye height is after we've applied the proper channel, which includes some losses for package models. So here's an example of how things have changed since the very beginnings of PCIe. On the left side, you see the eye opening of a 2.5 gig signal. Now, I can tell you, way back then, we were worried that we didn't have enough margin. So as we've progressed onward, the first 2, 5 gig and 2.5 gig, these were open eye specifications. So the majority of work that we did was about qualifying the transmitter signal quality. So we had a traditional eye diagram, et cetera. When we got to Gen 3, things changed dramatically, because PCI Express with a compliant channel is a closed eye specification. Well, that means that no matter how good your transmitter is, you could have 0 jitter. It doesn't matter. At the end of a channel, it's going to be closed. So that means we rely upon the equalizer on the receiver side to open the eye back up. So what you see here is a little bit different animal than these two, because this one has had a CTLE and a DFE equalizer applied to it to open the eye up. So what we want, that's where the BERT comes into play, because the BERT then is able to generate a signal that represents the worst case eye that a receiver might see. So for Gen 3, Gen 4, Gen 5, the BERT plays a crucial role in the validation and the achievement of interoperability. So on the receiver test side, let's talk about exactly what that is. So when we're doing a receiver test, what we want to do is to emulate the worst case signal. So we want to go to the worst case channel, which in Gen 3 is 22 dB at 4 gigahertz. We want to close the eye down so that the eye is about 42 millivolts of eye height, 0.3 UI of eye width. And we do that with a combination of ISI, random jitter, deterministic jitter. All of these components are added in what we call a jitter cocktail to the signal to create impairments. And we want to synthesize a signal that represents the worst case signal that a receiver might actually see. The process for doing that is probably the most difficult part of receiver testing itself, because you have to go through a number of different calibrations of different types of sources, impairments, and signals. And in the end, this is the output of the bird. Now you can say, well, that's not very clean. Well, is it supposed to be? So this is post-equalization. You can see that we're trying to achieve an eye height here that represents the target that we're trying to present to the receiver. So then the challenge is to take this eye that's generated by the BERT and to present that signal to the receiver and then put the receiver into loopback. And then we have an error detector on the BERT that allows us to count errors. And we can have, say, up to 1 error in about 6 minutes of testing. And that represents about a 95% confidence interval for achieving the target bit error ratio of 10 to the minus 12. So that means we're within specification for a receiver test. If we don't do this, or if we do a poor job at this, what happens? Well, your overall throughput's going to go down. You might have more retries, right? So your link might start to resetting. And so the overall system performance can degrade substantially. Even if it doesn't fail, it still can have significant problems that slow it down and make it operate at a speed less than what it needs to be. So for PCI Express 3.0, OCP 2.0, the BERT and the scope become crucially tied together. Because in the setup we have here, the scope sits in as a stand-in for your receiver. So we use that to help create this signal, right, this impairment. And so that goes together. And then once the BERT is properly calibrated, then we're able to run the test. Now, in addition, there are other tests that are done on the transmitter. This is the transmitter TX-PLL loop bandwidth test. So we want to look at what the clock multiplier circuit bandwidth is for different speeds of the device to make sure that that's compliant with spec. This is the transmit test. So you can see here we're driving a signal into the scope, and then we're applying either, we want to, in this case, de-embed the effects of the channel to move the reference plane to the output pin of the device under test. Now, Keysight has a couple of tools that are useful for doing this. This is a transmit test tool called the N5393F that runs on the oscilloscope. You can see one of the outputs is available, is shown right there. And then we have a M8020 BERT that we use to do the receiver test, and that's the other instrument that you see next to it. Now, for doing the setup, we first have to go through a calibration step. And so this is the calibration for PCI Express Gen 4, and we're using Gen 4 test fixtures in this case. So this would be consistent with OCP, plans for OCP 3.0. Now the overall test requirements for receiver test include that we include 2 types of testing. I mentioned there are different specifications that the PCI SIG has written around PCI Express. One is called the base spec, which is really a silicon spec. So if you're developing IP or if you're developing chips, then you test according to the base spec for the receiver test. The calibration process for a system test, like you see here, is completely different. So it's similar in that we follow the same overall approach, but the actual targets and the methods for how we put together the jitter cocktail is a bit different. So both of those testing tools are available for PCI Express testing for Gen 4. And here you can see the complete set of tools that comprehend both testing for Gen 3 and Gen 4, from testing the channel to the transmitter to the physical layer and receiver, and then also for Gen 3 for doing protocol test, where we can actually look at the link once it comes up. If you have interest in additional information, you can get that from Keysight.com, and you can download this presentation from here. So with that, I'll turn it back over to Samit. And, oh, John, you're going to do this. Okay.
Thank you. Thanks, Rick. So I'm kind of the beginning and the end. So we're nearing the end. We'll get some questions out of there, but we wanted to talk a little bit about future work from what you've just seen. Because one of the things that we wanted to do is bring some hardware, let you play with it, and then get feedback. I'm speaking of the validation, get feedback on where we need to be so that we can get this done and contributed to the community before the 1.0 spec later this year. That way, when we get a 1.0 spec, you've got a defined test and validation strategy for electrical, mechanical, and thermal. So, pardon me. What do we need to do? So on the OCP2, I skipped one? 3, thank you. I knew I didn't know if we did 2 or 3. Anyway, we need to release some conformance guidelines. As Sumit said, there's a subgroup or a subgroup of people working on it that I hear is going to get larger, and that's great. One of the things that I think everybody has said, this is an open community. To use an IEEE phrase, it's not a spectator sport. It only moves forward based on contributions from the member companies, and we value everyone's opinion. And I think Josh said we did 14 enumerations initially, and it was great. Everybody kept bringing things together, and we finally got the last one is what we chose. One of the things that we wanted to be able to do that from my Ethernet exposure is enable a third-party lab. So UNH-IOL is the premier third-party lab for Ethernet in the world. I don't think anyone will question that. They've done a great job for many years. We have a representative here, Curtis Donahue. They are working with us to try to develop a conformance program at UNH-IOL that companies can take their systems and adapters to and get actual conformance. And maybe that would expand into something else. We need community involvement in order to make that happen and make it something that you and your companies would want to use. And we want to enable the test automation. Rick's covered a lot of that, trying to make everything very similar to how PCI SIG is doing this so that those tools and that automation will work. For OCP2, they're targeting the second quarter of 18 to get the guidelines done, establish the acceptance criteria, and get the fixture designs out. So the complete package of what you'll need and contribute that there. For OCP3, we're running a little further behind because we're going to do OCP3 and we're going to encompass not only Gen 3 but Gen 4, and we're going to look ahead toward Gen 5. We've been promised by our connector vendors that Gen 5 is not out of the question, and I will get to why those connectors aren't here today in just a minute, but it's not really part of this. And you know, hopefully with UNH-IOL's help, we're going to be able to enable not only UNH-IOL as a third-party lab, but have them enabled other third-party labs throughout the world. That's an ODM. Whoever wants their lab certified, they can get that from UNH-IOL and actually say, yes, we conform. It's something that we've done in other areas, and it seems to be very successful and very well received. The PCIe Gen 5, just to mention on it, it's at a draft stage. The 0.9's due out later this year. We did take into consideration, Josh showed you the 50-50 and the 90-10, and it was one of the 50-50s. So we took our best stab at what it's going to take to make it Gen 5 capable, because when you start looking out 2 to 3 server generations, Gen 5 is a reality. There's a lot more work that needs to be done in that area to see if we really succeeded in there and what it would take. You know, what type of materials that we're going to take. Are the connectors sufficient? They may not be the weak link, looking at the data that has been floating around from the connector suppliers. And so I think that we have a good chance of making this work at Gen 5 with some restrictions potentially on the routing. So, Keysight, they're already in the hunt there for PCIe Gen 5. They have the tools. This deck will be released. And then we have a demo that Keysight has been kind enough to present. I mentioned it earlier. We'll have it running for a little while. I don't think we'll get kicked out of here right at 3. And I encourage you to stop by and see it. It's very impressive. Submit and the team that did all the test fixtures and Keysight did a great job getting that working. So if you wonder why the connectors did not make it here, there's been this maniac around Austin planting bombs. And so all of the carriers are now x-raying every box. And the box with the connectors didn't make it out yesterday. So they're going to arrive tomorrow, and none of us will be here. So that's what we had. Do we have any questions for Sumit, Rick, or myself? Ken. So I don't know if Ja's here. I think he had to go. Okay. So there's no planned updates today to the OCP2 spec. So this is being done to develop an ecosystem. We have to work with Ja to get that in the plans. But for existing cards, as a system vendor, we're going to put requirements on you based on what's industry standard, and where we pick that up is going to be dependent on how successful we are at the current moment. So I don't think there's a date. I think Sumit's done a good job of estimating when he's going to have the guidelines and things available. How that gets rolled into the spec is not been determined with the.
So that's like, I think for 2.0, it's a little challenging because we have the ecosystem out there. So it's a more of retroactive work, what we're trying to do.
Submit.
And the 2.0, oops. So 2.0 work was, as John was indicating, is mostly to help us develop the ecosystem for, or give us the learnings for 3.0, what do we need to do. So we are using this as a learning platform because I think as Rick indicated, there's so many intricacies in there for the PCI compliance testing, and the OCP topologies are so different, the channel topologies, it's very hard to really define at this point for 2.0. But I think we'll probably have to, we can circle back.
Yep. So it may not be that 2.0 becomes a requirement before 3.0 spec is released, but the group working on this is trying to get all of this in for the 1.0 spec release later this year. I'm sorry? Of 3.0, thank you, yes. So a couple other little items is we also have a large form factor thermal test vehicle. And in the spirit of enabling the ecosystem, not only for OCP3, but OCP2, Dell did an OCP2 thermal test fixture several years ago, and we're going to also contribute that. Again, may not be required, but at least there'll be something up there. If companies want to use it, then it's consistent with the 3.0 large and small form factor thermal test fixtures. Other questions? Thank you very much. Again, please contribute.